Okay, here we go. So today we're going to be reviewing the Moody diagram. And we're going to be using it to solve pipe flow problems. And they're called type 1, 2, and 3. Based on kind of what we're asking for, what's the known, what's the unknown. And so our learning objectives today . See if I can get a little grid going on here. See if this helps. We're going to calculate friction loss, energy loss due to friction or friction loss in a pipe using the Darcy-Weisbach equation, which we introduced last time. And then we're going to use the energy equation to solve pipe flow problems. Okay, first let's review the energy equation. This is something that we're all committing to memory. This is everything. Everyone's going to be getting a tattoo of this. You can choose where, it's fine, but it just has to be the energy equation. Who remembers the energy equation? From point 1 to point 2, right? Energy at point 1 is equal to energy at point 2 plus head loss. Right, so Bernoulli is no head loss or no energy loss. Energy equation is, you just add on that energy loss term. So we'll write it together. We'll say it together. Ready? P1 over gamma plus V1 squared over 2G plus, we'll just say Z1 is equal to P2 over gamma, I can't hear you, plus V2 squared over 2G plus Z2 plus head loss. We'll call it, which we call right now, we'll just keep head loss as head loss due to friction. And also known as major losses or major loss. So let's just do a quick energy equation example, then we'll get back into head loss. So this is example 3.3 in your book. We've got a 25 centimeter diameter horizontal pipe. The flow rate is 0.16 cubic meters per second. And the pressure that we measure in there is 200 pascals, which is just Newton per meter squared. And then our elevation of that pipe is 10.7 meters above sea level, or mean sea level. Calculates the total head. Or total energy in that pipe using the energy equation. So why don't you all do that? I take a sip of tea. It's not very good, but it keeps me awake. It's mate. Yerba mate. Coffee in the morning, tea in the afternoon. Okay, so we the total head, and all we're just doing is plugging in some numbers here, right? So we're just saying we got to mind our units, but the units are pretty friendly. We're keeping everything, you know, kind of in newtons and meters, etc. So 200 newtons per meter squared. We'll assume we're not given any specific information here, so we'll assume kind of standard conditions. So we'll just say 9,800 newtons per cubic meter plus our velocity, Q over A is equal to velocity. Okay, so we got our kinetic energy term, and then we just add our Z. So all that should come out to be 11.3 meters. So we'll note that the biggest energy term here is the elevation term. That kind of trumps everything. The velocity term, I didn't actually calculate this out individually, but the kinetic energy term is, you know, a tiny portion of that, and the pressure energy term is a tiny portion of that. So let's get back into these major losses here. So H sub F, we defined the Darcy-Weisbach equation last time as this friction factor over L over D. So length, diameter of the pipe, V squared over 2G. So we abbreviate this as the DW equation. And we use the Moody diagram to find our friction factor. So F is a function of the relative roughness height, E over D. So this is, for Ryan, this is the roughness, the height, the actual measurement of the roughness elements inside of a pipe. When we look that up in a table, we divide by the diameter of the pipe, as well as the Reynolds number, which tells you, is your flow turbulent or not? Does anyone remember what the Reynolds number is? So kind of, yep. So kinematic viscosity. So velocity of the flow, diameter of the pipe, times or divided by the kinematic viscosity. So the greater the viscosity, the lower the Reynolds number for a given velocity, right? So the thicker the fluid is, and we're just dealing with water in this case, but it is a function of temperature. So as temperature increases, viscosity goes down. As temperature, did I say that right? As temperature increases, velocity goes down. As temperature decreases, viscosity goes up. And so that means that for really cold water, it's less likely, or it's going to be, the Reynolds number can be lower and less turbulent because it's thicker, quote unquote. It's more viscous. Great. Let's take a look at the Moody diagram one more time, and then we'll go into doing these problems together. So last time see if I can sketch on this. Last time we used the Moody diagram to figure out what the friction factor is. So the friction factor is over here on this axis, on the left-hand y-axis. And this tells us, kind of given a flow rate and relative roughness height, Reynolds number, how much energy is being lost per unit length of pipe. So we calculate the Reynolds number. So if we know the velocity and the flow rate and the diameter and a temperature, we can calculate the Reynolds number. And then we can know the pipe element type. So is it a steel pipe, a plastic pipe, a concrete pipe? We look up that E value in a table, divide by the diameter, get a number, and then we find where the Reynolds number intersects a blue line associated with a relative roughness value. So say for a given flow rate, this is our Reynolds number, 10 to the 6, and say this is our relative roughness. Then I'm going to trace up until I hit that blue line that starts at that value of relative roughness. I'm in what's called the transition zone, where this line is curvy. If, for example, I were over here at, say, 2 times 10 to the 7th, then I'm in this kind of flat zone where the friction factor is a constant, or kind of is just a function of Reynolds number and this friction factor. And I would trace this all the way back over to find my friction factor right here. And then here it's just slightly greater over here. So this is the friction factor that we would use to plug into the Darcy-Weisbach equation. We also introduce the Swamee-Jain equation. I won't write it out here again, but this essentially replaces the Moody diagram. It's kind of a bear to put in your calculator, but we can use it to calculate the friction factor. And all it says is you need to know the relative roughness and the Reynolds number. You plug those values in and you calculate that friction factor value directly. Okay, so that was the foundation from Tuesday. Let's start doing some problems together. So we're just going to define them as types. So type 1 is you are given the flow conditions. Either a discharge or a velocity and you're given pipe specifications. The material type, the diameter. And then what you want to calculate is calculate delta P or HF. And the reason these two are related is that as we lose energy in a system, it manifests as a change in pressure, as a reduction in pressure. And we'll be measuring that, for example, over in that lab device, the pipe bend device that we'll use later. So the idea is you've got a pipe. You've got flow coming in. The pipe has the same diameter over here as it does over here, even though I didn't draw it that way. And if we measure pressure 1 and pressure 2, we'll note that pressure 1 is less than pressure 2 because of H sub F. And so we have this hydraulic grade line that we introduced, right? This is, if we were to put a manometer in here and see how far the water came up based on the pressure. Based on this distance here, we're going to have some drop in pressure due to friction. So that's what we're calculating. A type 2 problem is given a change in pressure or a head loss and our pipe specs. Calculate a flow rate. And then the final type of problem is we'll be given Q or V and delta P or HF. And we will find the required pipe diameter. So this problem right here, we can solve directly. It's an explicit solution. It's just plugging and checking. These two problems have iterative solutions. Because, as we'll find out when we do an example in a minute, calculating the flow rate is going to be based off of some energy loss or something like that, and that energy loss is based on the flow rate. So we'll show how to do that together. Okay, so let's do a type 1 example together. Okay, so water flows at a rate of 0.02 cubic feet per second. Through a horizontal pipe that is 500 feet long. Made of galvanized iron. And the diameter is 3/4 of a foot. Or sorry, is that inch? It says inch. Yep, 3/4 of an inch, tiny pipe. I guess that's not so, it's pretty standard. 3/4 inch pipe. Calculate the pressure drop. So always a good idea to draw everything out. So let's go ahead and draw our pipe. And we'll say this is 0.1, this is 0.2. All right, now we're going to get into this rhythm here with the energy equation. So let's do it together. What we're gonna do is do the energy equation from 0.1 to 0.2, and then we're gonna solve for what we need to solve for. Okay? I want to hear all the voices. I want to hear Simone in the back. Stand up and do it. It's like choir in church. Okay? P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 over 2G, D2 squared over 2G plus Z2 plus head loss. Good job. Proud of y'all. Next time it's going to be even louder. Okay, we'll write our Darcy-Weisbach equation. Head loss is equal to the friction factor, L over D, B squared over 2G. And we want to find delta P, which is just equal to, we'll say P1 minus P2. All right, so what do we do? Yeah, can we cross some stuff out? Okay, elevations cross out horizontal. What else can we cross out? Velocities, because the pipe diameter doesn't change. Water does not slow down. If it did, then it would stack up and there would be an explosion. I don't know. It doesn't really happen unless there's a water hammer when it does happen. But we'll talk about that later. Okay, so we got to cross a lot of stuff out. That was nice. And we end up with P1 minus P2 if we bring those over, right? So let's say P1, let's do it in black. Is equal to our major losses, which I'll just write out. F L over D, B squared over 2G. We'll bring that gamma over here, and then we got our delta P, right? Okay, so this is pretty basic. It's a thing that we can directly solve. And let's just do it together. So delta P is equal to F L over D, B squared over 2G gamma. We'll go ahead and say gamma because we're in British gravitational units or US units, 62.3 pounds per cubic foot. So what, do we have all these numbers? Do we have all these values here? We don't have the friction factor. We need to solve for this, and we'll use the Moody diagram to do that. So what do we need to know to solve the friction factor? We need to calculate the Reynolds number. So Reynolds number is equal to V over D over viscosity. And the other part that we need to know is the relative roughness height. So, so part of this is solving for velocity. So let's go ahead and do that. So velocity is equal to Q over A, which is equal to 4Q over pi d squared. So 4 times 0.02 cubic feet per second, all over pi times 0.75 over 12 feet. Squared. So just converting that inch to feet and then squaring that, and we end up with velocity is 6.52 feet per second. Okay, so we got that part. We need to know the dynamic viscosity. We can look that up in our book. It's in chapter 1, that table. Assume, what are we assuming here? Is it standard or normal conditions? Does anyone have their book? That chapter 1? Let's take a look at that table. Okay, let's bring that up. Moody diagram. Yeah. Okay. 1.08. That's the number I have down in my notes. So that's 60. So that would probably then be normal conditions. Okay. All pretty close. So for our dynamic, or sorry, kinematic viscosity, it's 1.08 times 10 to the negative 5th feet squared per second. Okay, so we can plug that in and calculate the Reynolds number. Let's go ahead and do that. So plug those values in. We've got 6.52 feet per second times 0.75 over 12 feet. All over 1.08 times 10 to the negative 5th feet squared per second. And our Reynolds number comes out to be 3.8 times 10 to the 4th. Dimensionless. E over D. It's not rocket science, but it takes a long time. We can look that up in the table. So it's galvanized iron. Should be a table that you have in chapter 3, table 3.1 perhaps. Oh, we got that in the Moody diagram. Great. Let's check that up. Galvanized iron, 0005 feet. Looks good to me. So 0.0005 feet all over. I should have just calculated D, but here we are. 0.75 over 12 feet. So go ahead and calculate that. We get relative roughness of 0.008. Okay, now let's go to the Moody diagram. Could have been going there all the whole time. One-stop shop. Okay, so 008, this is our line to use. Let me use a different color here. This is the line we're going to use, but we're way over here. We're at about 4 times 10 to the 4th, right? Kind of a low flow rate, narrow pipe. So we're going to trace all the way up until we intersect this line. Ooh. Right there. So that's our intersection point, and it's pretty much right on that value right there. Oh, okay, we made it. That's brutal. Okay, so this is 10 times 10 to the negative 2. So this is about 3.7 times 10 to the negative 2. That's our friction factor. Based on the Moody diagram. So it just went up a little bit. It would have been 3.6 if we were fully turbulent over here. All right, we good? So friction factor, 0.037. Okay, so now we've got all the things that we need. It's just plug and chug, but it does take a lot of steps to get there. So delta P is going to be equal to our friction factor times our length over our diameter times our velocity times 2g finally times our gamma. Let's do the units, because why not? Cross those speed outs, we get the second squares, cross outs, and we get feet squared, right? So then this ends up crossing out, those cross out. Feet squared divided by feet, so we end up with feet squared on the bottom. So delta P is equal to, I get 1.2 times 10 to the 4th pounds per foot squared. I'm going to do a type 2 problem now, and this is where it gets iterative. So we'll draw some reservoirs. We'll be doing a lot of these kinds of drawings. We've got a reservoir, it's got a pipe. Flowing to another reservoir. got water. There's an elevation difference between them. And then we're going to be given some, oh, there we go. We're going to be given some details. So water is flowing. We've got two elevations in the different reservoir. You can think of these as really big, so that elevation isn't really moving that much. It's pretty static over time. And we've got an elevation difference of 10 meters. We've got a pipe diameter of 0.5 meters. We know that the length is equal to 700 meters. And that the material is cast iron. Cast iron is really common from the last many decades. They're not really using it anymore. They're using plastic pipes for the most part. It's still being used, but it's often being replaced. But so we'll see a lot of problems with cast iron. Just saying. So we're want to find, so we're kind of given this information, and then the question will be to find the flow rate between the reservoirs. So as with all of these problems, we're going to use the energy equation and we're going to solve it between 2 points. If you were to use this energy equation, what points would you pick on this problem? Water surfaces. And why would we do that, Haley? Yeah, so we can say that at the water surface, P1 and P2 gauge equals 0, atmospheric pressure, right? So that kind of simplifies the problem. What other things can we simplify here? And if we're on a reservoir, we're assuming that the velocity is essentially 0, right? So velocity negligible. Negligible. So V1 and V2 are approximately 0. This really simplifies things for us. Now we could pick any point in the reservoir and it would end up being the same type of problem. So if we picked one here, right, 1A, and if we picked 2B right here, just to kind of talk about it, we could use the hydrostatic pressure equation to calculate the pressure. If we knew how deep you were, right, you're 5 meters down over here, we can calculate the pressure and the elevation, all that. But it's all going to equal out, right? Because you're going from here, it's just like the manometer problem. You're going from here, you got some energy losses, you're going back up to here. So you could do that and prove it to yourself, but it's just going to complicate matters. So it's arbitrary which points we pick. Might as well just pick the surface. And yeah, okay. So I think that's enough to say about that. So let's do the energy equation just because we're learning it. P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 over 2G, V2 squared over 2G plus Z2 plus our major losses. We already said that we can cross out our pressure terms. cross out the velocity terms. And so what we end up with is delta Z is equal to the head loss. If there were no head loss, then the two water surfaces would be equal, but we do have head loss, so therefore they're. So we've been given this water surface elevation, so we know that 10 meters is equal to our head loss. This is getting real simple, right? But now we need to actually calculate that head loss. So let's look at that Darcy-Weisbach equation. So to calculate the head loss, we need to know the velocity, right? And to calculate F, we need to know the velocity. So now things are going to get a little more interesting here. What we end up having to do is we have essentially an unknown that we need to solve for, two unknowns. F is an unknown and V is an unknown. So two unknowns means we need two equations, right? Our first equation, we can just base it off of this. And so we'll just kind of say equation one. And what we'll do is we're going to solve Darcy-Weisbach for velocity. So let's go ahead and do that. So we'll just bring all those terms over that we need to and isolate the velocity. Okay, so that's equation one for us. And what you can do to kind of simplify this for your calculations is to plug the numbers in to kind of simplify everything, because we're going to be using this a couple times. So go ahead and plug all the numbers in. So we've got 10 meters times 2 times 9.81 times 0.5 meters divided by F times 700 meters. So we'll simplify that equation. We get 1 over square root of F times 0.374 meters per second. So when we're working with multiple equations, it makes sense to reduce them, to simplify them, because you're going to be punching these numbers in a calculator a couple times. Okay, so what's going to be our second equation? Where do you think? What else are we going to use in this problem? Reynolds number. Okay. And then we're going to basically, so we're going to use the Reynolds number equation to solve in terms of velocity. We'll just give you the kinematic viscosity 1.00 times 10 to the negative 6 meters per second. We'll plug our numbers in. So Reynolds number is equal to 0.5 meters meters squared per second times velocity. Okay, so this is our Reynolds number equation. So now we've got two equations and two unknowns. We just have this little funny F term in there. So once we've got those two equations, I'll give you the algorithm for these type 2 problems. So type 2 algorithm. First, we're going to guess an initial value of F based on what assumption do you think we're going to make? Let's go look at the Moody diagram real quick. If we were going to guess a value of F, what would it be based off of? A relative roughness value, and then what other assumption? Fully turbulent. Great. So we can calculate, we have the pipe properties, so we can calculate that value. And then we assume fully turbulence. That means that our friction factor is just a direct function of the relative roughness value. It's in this flat zone. So assuming fully turbulent. Okay, now we're going to use equation 1 to solve for velocity. Then we solve for Reynolds number using equation 2. Calculate a new F, so F1 using the Moody diagram, based on that relative roughness and your Reynolds number that you calculated. Compare your initial guess of the friction factor and F1. And then if they're the same, great, you're done. If they're not, then iterate. Yeah. You know, for these problems, we're using a visual, you know, a graphic, the diagram. And so I would say, you know, if it's plus or minus, yeah, let's just look at the Moody diagram. Okay, so our initial guess, say, is 3.1, and then you iterate and it's 3.2. Then I would do it another time. But if it's kind of indistinguishable, then don't do it another time. Meaning, like, if it's less than half the weight difference. If you were to round it, right? So you might iterate one time. It usually converges over 1 or 2 iterations. So let's do that real quick. Okay, and what I'm going to do is write out a table, and that'll help us do our iteration. So first we'll do F, then we'll do velocity from equation 1. Then we'll do the Reynolds number from equation 2. And then we'll get F, or just say new F, Fi plus 1, right? So we need E over D, and we'll just, for the sake of time, give y'all the E. So E is for cast iron, 0.26 millimeters. And then E over D is so 0.26. (5.2) times 10 to the negative 4. So we'll just write that out, 0.1235. That's the best we'll do for that Moody diagram table. All right, so we'll take this number, we'll go to Moody, see what's up. We had 3 zeros and a 5, so that brings us to right here, assuming fully turbulent conditions. Trace that over, and I get 0.017. Does that look right to you? So our first guess is 0.017, assuming fully turbulent conditions. Let's go ahead and use equation 1 to solve for that. So 0.374 times 1 over square root of f. We get 2.87 meters per second. Plug that into our Reynolds number equation and solve for Reynolds number. 5 times 10 to the 5th v. 1.4 times 10 to the 6. Okay, so now we have a Reynolds number. Let's go ahead and back to Moody and see what's going on there. 1.4 times 10 to the 6. Okay, so here is 1 times 10 to the 6, 0.2, 0.4. Take that all the way up. And then here was our original E over D. And so the way we do this again is you take that flat line and then you just start to curve it up and basically do a visual linear interpolation. Ooh, something like that. Probably should be a little bit higher at that point. So here we go. And you can see it's like based on that visual, it's not a ton higher, but it's a little bit higher. I'm going to say it should be right about there. So we'll come across and we'll say that it's 0.0175. You can use the Swamee-Jain equation to double check. So we bring that over here and then do it again and kind of see what we end up with. How far off are we in terms of Reynolds number? Calculate that velocity. This time I get 2.83. Reynolds number 1.4. It doesn't change the Reynolds number that much if you just stick to 2 significant figures. So we'll say that our new F is 0.0175, and we'll call it good. So you can kind of use the precision of the Moody diagram to determine how many iterations you do. We saw that we weren't fully turbulent, so you do want to correct the F a little bit for that condition. And the F went up just a little bit for that. All right, so now we've got a new velocity that we'll use. So 2.83, and we can calculate our flow rate. So Q is equal to velocity times area, 2.83 meters per second times our, so pi d squared over 4. Ooh. And we end up with 0.56 meters cubed per second. So ultimately, we wanted that velocity, but you could go back and use this to calculate the actual head loss, if that were the question. Although they gave you the head loss with it. Another way to check yourself, right? You could say, what does the Darcy-Weisbach equation give me for head loss? Does that compare to 10 meters using this F that you found? Way to check it. Great, so that's a type 2 problem. You know, it starts out with a very simple equation, delta Z is equal to H sub F, but then we get into this whole can of worms here. I'm gonna set up a type 3 problem for you, and then I think we'll solve that at the beginning of class next week. But if you guys want to just take a go at it, you're welcome to. So here it is. It's just a little bit more complicated because there's basically some more steps to iteration. Okay. So we've got that reservoir again. Got a pipe. Got water in it. Free surface. We're going to look at 0.1 and 0.2. We know that our length is equal to 500 feet. We know that the elevation difference in the reservoir is 80 feet. So that's going to be our head loss. And note that last time I didn't say it explicitly, but when you're doing Z1 minus Z2, you're assuming that this is the data essentially, right? So delta Z is equal to 80 feet. Anyway, just something to note. We know that this is a commercial steel, so that's a item you can look up in your table. Commercial steel is the pipe that we're going to use. And we need to we know a flow rate, so we need to be able to deliver 3.5 cubic feet per second. So this is based on, say, okay, we need to supply this to, say, the water treatment plant or something like that, based on the average daily demand. Okay, so we know the flow rate, but we need to design the diameter. So find D. What's the diameter? How big of a pipe do we need to meet these conditions? So what we're going to do is calculate it, and then you're basically going to round to an integer. Maybe it's going to be the nearest 6 inches or something like that, right? Based on available pipe sizes. Okay. So I'm going to give you the way to solve this, and then we'll pick it back up next time in class. So what we'll do is first we're going to have equation 1, which is going to be diameter is equal to a function of F. And that's using the Darcy-Weisbach equation. And then our second equation is going to be very similar, right? In this case, its Reynolds number is equal to a function of diameter, because we know velocity. And then here's your algorithm. We're going to first guess D, so D naught. Then we can calculate E over D. Then we can calculate the Reynolds number based on D, right, from equation 2. All right, now that we got that Reynolds number, we can get F from the Moody diagram. And then once we get that friction factor, we can go back to calculate D1 or I plus 1 from equation 1. So D I plus 1 goes back over here. And then we continue. So this one's got it's got another step or two in it. So it's a little more complicated. And where do you start, right? Do I pick 12 inches? Do I pick 18 inches? Fortunately, this iteration, maybe it takes another step or two, but it doesn't matter that much where you start, as long as you don't say 100 feet. So start with a foot, right? And then go from there. All right.